Hi everyone, my name is Mengbai. Today it's my pleasure to present Mixer, the next generation search engine we designed in Baidu for visual content retrieval. This is a cooperative work from both academia and the industry. The authors are from Baidu, Shandong University, and the Ohio State University. The internet today is video dominant. Modern web pages are composed of not only the text, but also the visual objects like images and videos. For example, a news page at the left side contains the article and also a figure and a video. Another case is the web page to deliver the video content, like YouTube, where the comments and the textual description are also helpful to the users. As a result, a modern search engine must be capable of understanding and retrieving the visual objects. To achieve this, we designed Mixer, which is responsible of handling the images and the videos crawled from the internet. In Baidu, Mixer is placed on top of the infrastructure systems, like our distributed storage system, and below the applications. Mixer serves our image and video related applications, like the image to image search or the video recommendation. And worth noting that Mixer is besides a conventional processing pipeline for text-based search. It means that when a web page is crawled from the internet, it is decomposed into textual information and visual objects, which are processed individually. In Mixer, two major components are implemented: the visual content understanding and the visual content retrieval. Thanks to the fast development of the deep neural network, we can understand the visual object effectively. However, using the DNN models for feature generation are computation intensive, and the different features have to be produced with different models. As a result, it is not practical to process an image or a video with all models we have, which is computationally unbearable. So we train a CNN-based classifier to categorize all visual objects into classes, including scenery, movie, portrait, and others. For each class, different features are generated. For example, we may want to recognize the actor names and determine the clarity score in a movie. As we generate multiple features for a visual object, we use a compound feature vector to contain them. In addition to the visual features, we also hold features that are not generated by the DNN models, like the resolution of the video or an indicator telling if the resource is dead. A feature in the compound feature vector is produced by a feature production model. For example, to detect if any commercial logo embedded in a video, we could combine three operators: sample, OCR, and logo into an FBM which takes a video as the input and outputs the result yes or no. In order to incorporate the state-of-the-art development from the machine learning community, we also designed a full-fledged model production subsystem for the FBM. In the subsystem, a model developer is allowed to upload and test their models in an agile and responsive way. These models are managed in a pool so that Mixer could deploy them in a production environment on demand, allowing fast iteration of the model updates. In addition, AutoML and TensorRT are adopted to support the developers. With such optimizations, we increase the model production speed by about 2 times, increasing from 6 models per month to 12 models per month. When deploying and executing an FBM, Mixer schedules the operators and directs traffic according to the edges. A heuristic algorithm is designed to schedule the operators. In the algorithm, we activate the operators from the source to sink, since no data will arrive at the sink node at the beginning stage. For detecting the bottleneck in a running FBM, we experimentally devote resources into the operators from the sink to the source. Whenever we find the overall throughput is improved, we keep that change and start from the sink again. Feature vectors are generated and stored into index files after the content understanding. The next step is to retrieve the similar images upon a query. The image retrieval layer is designed to accept a query vector, which could be a SIG feature, and returns a list of similar images. In the image retrieval layer, vectors are encoded with product quantization. Compressing a 1024-byte SIFT feature into a 128-byte vector could improve the throughput by 3 to 4 times. The insertion performance is another major concern in Mixer since we keep running a large volume of images and frames. In addition to the base index file, which groups the neighboring vectors, we use the write-ahead log to contain the newly inserted vectors. When a search happens, both the base index file and the write-ahead log are used to locate the candidate vectors. Above the image retrieval layer, the video retrieval layer is designed as a video-to-video search framework, where image is also a legal query and is processed as a video with only one frame. The task could be finding duplicate videos or searching a specific people among videos. To locate the candidate videos, we extract keyframes from the input videos and exploit the image retrieval layer to find the similar frames. The videos containing these similar frames are then marked as the candidates. Additional steps are adopted to further refine the candidate video list. In the candidate refinement stage, Mixer filters out the edited videos like a video concatenates small clips or talk show duplicates frames from another scenery movie as its background. The last step is to rank the candidate videos, which relies on the similarity scores of all frames. To comprehensively assess the visual resource retrieved, we need to consider all relevant resources, such as the same video encoded in different resolutions. All the player pays at different platforms. We thus name the process of locating the relevant resources as aggregation retrieval. We will not present the details here due to the time limits. Please check our paper for details of the aggregation retrieval. In the evaluation, we first compare our heuristic scaling algorithm to the fixed quarter algorithm when executing a feature production model that recognizes the city names appearing in a video. We select this model since all operators could be either executed on GPU or on CPU. The result of our algorithm is presented in the table, from which we can see the heuristic algorithm improves the processing throughput by around 8 times. We also break down the resource provision in different stages, and the details are shown in the figure. For the fixed quarter algorithm, we can see that the same amounts of resources are devoted into the operators during the execution lifetime, while with the heuristic scaling algorithm, computation resources are allocated dynamically. For example, the BERT operator is close to the sink, and we can see almost no resources are allocated to it at stage 1 and 2. As the data flow to BERT in stage 4 and 5, a large portion of computation resources shift to this operator. We also evaluate the retrieval cost of the VR layer, which is measured in cores per million video QPS. This indicates how many cores we need to devote for maintaining 1 QPS over 1 million videos. The costs are measured whenever 200 million videos are added into the database. The results are shown in the figure. When the database scale is 200 million, the cost is as high as 270 cores per million video QPS, but it quickly decreases due to the numerous engineering efforts we have made during the system development. As the database scale reaches 600 million videos, Mixer gets into the mature stage and the cost eventually converges at 7.2 cores per million videos QPS, showing the excellent scalability of our system design. To conclude, Mixer is an advanced search engine towards understanding and retrieving visual objects at web scale. For content understanding, a full-fledged subsystem is implemented to help model production, and a heuristic algorithm is developed to optimize resource provision in model execution. For content retrieval, an image retrieval layer as well as a video retrieval layer are combined to handle diverse retrieval tasks, and the aggregation retrieval is adopted to improve precision and recall. That's all. Thank you.